Welcome to video lecture M4. This is about linear transformations in practice. I'm your MC, Tom Roby, and here are the outline and objectives. First, we need to memorize some things in mathematics, particularly definitions, and here there are fundamental properties that linear transformations may or may not have. They're called one-to-one and onto. So by the end of this, I'd like you to be able to interpret them geometrically and recognize them in concrete examples. Then we'll connect these concepts with properties of the columns of a matrix representing a transformation. And finally, we'd like to be able to analyze whether a given matrix transformation has these properties or not by converting it to the row-reduced echelon form. But before we even talk about linear transformations, it's worth pointing out that the concepts of one-to-one and onto are quite general, and they occur all over mathematics. In particular, they're really important for understanding whether a function has an inverse or not, right? We know that if you've had multivariable calculus, for example, there's a whole inverse function theorem. And in general, often some things in mathematics are easier to go one way than the other. For example, it's easy to multiply a matrix times a vector and get some output. It's not so easy to figure out, is there a vector which when you multiply by the matrix gives you that output, right? And so that becomes solving a system of linear equations, and it's much harder than just plugging in values to see what your output is. So before we get at inverses, we look at one-to-one and onto. And let me just give you some very simple examples, right? So what does one-to-one means? Function f is called one-to-one if whenever f of x equals y in the target, in the codomain, then that means the things had to be equal in the domain itself. So you can't go from two different places into the same place. If you do that, it's not one-to-one. Another way of thinking about it is if x is not equal to y over here, then f of x is not equal to f of y over there. And it's called onto if everything in the codomain gets hit. So let's do some really simple examples. And maybe I'll draw the blob first. So what does the blob picture of this look like? So the blob is that I've got some space x, some set x, and I've got some set y. Now I called it z, I guess, right? So I've got z over here, and this is an example of not one-to-one, right? So one-to-one is when that doesn't happen. Okay? And onto, what does onto means? Onto means that when I look at where this goes, I look at everything in x and I say, where does everything in x go? That it somehow fills out everything here. So no matter which z I pick in here, I can always go back from that and find some x that map me to z. So that's what onto means, right? And it's clear that not every map will have this. Let's just look at some very simple examples, right? If I have like the set, if my set is 1, 2, 3, 4, and I map over here to A, B, C, right? Now because it's a function, everything over here has to be mapped to something, right? So I try to make it one-to-one. Maybe I send 1 to B and 2 to C, and, 2 to A, 1 to B, and now 3 or 4 has to go to C. Suppose 3 goes to C, 4 has to go somewhere, and wherever 4 goes, it's not going to be one-to-one. Okay? So there's no way to make a function where I've got more elements on the left in the domain than I have in the range. There's no way to make that one-to-one. Now, of course, when I'm talking about linear transformations, there are infinitely many points on both sides, but we're trying to understand this in simple examples. On the other hand, this map is onto, although it didn't have to be, right? I could have sent all of 1, 2, 3, and 4 could have been mapped to A, and I could have left B and C alone. So it's possible for a function to be neither one-to-one nor onto. That happens quite a lot. And now if I think about another possibility would be maybe I've got 1, 2, and 3, and I'm mapping them to A, B, C, D. Right? Now think about it for a minute. Could a function that does this be one-to-one? Could it be onto? Well, it could be one-to-one, right? I could just send 1 to A, 2 to B, 3 to C. That would be one-to-one. As long as I send them all to different things. It doesn't have to be. I could send them all to A. But it can't possibly be onto, right? Because I can't send one to more than one thing. So no matter how I do it, I have to leave something out. In this case, I left C out. So there's no way for this function to be onto. So this is not onto. Although it is one-to-one. Right? And this function over here is onto, but not one-to-one. And if I want a function that's both one-to-one and onto, I'll actually have to have the same number of elements in each set. So I'll have to do something like I could have a bijection between 1, 2, 3, 4, and A, B, C, D. Right? And there are lots of different ones. In fact, there's 24 of them. Lots of different choices for this. But there are a lot of different ways that I can make this one-to-one and onto. Sometimes these are called bijections, or permutations in the case of finite sets. OK, so I hope that made some sense. So just to give you a less formal thing, we'll say a mapping is one-to-one if every z and z is the image of at most 1x and x. Right? So here, this is not one-to-one because b is the image of both 1 and 4. But here, this is one-to-one because a, b, and d are all the images there's a unique way to figure out where they came from. And you can see how that would be useful for defining an inverse function. Okay? On the other hand, a mapping is onto if every z and z is the image of at least 1x. Right? So here it's onto because there are two things that b came from, but at least I can find something. Right? I can find it came from 1 or 4. Now over here, c didn't come from anything. So you can think if you're trying to define an inverse function, it would be useful to be able to know where something went to. Now, of all these situations, this is the only one where I've got a nice function going forwards and backwards. Okay? So to some extent, one-to-one and onto are properties that you need to have both of if you really want to have a proper inverse of a function from one set to another. One-to-one is enough if you want to just define it locally. So if I just wanted to define an inverse on A, B, and D and could leave C out of it, that would make perfect sense. Okay. So let me show you some examples of functions back from calculus days or whatever, or even earlier. We dealt with a lot of functions from R to R, right? And typically, even though lately I've been drawing functions that look like, you graphs that look like this, where I'm going from one of these to another, typically, when you had a function from R1 to R1, then you would just make this the domain and this the range and draw them on the same set of axes, right? So, one example, what's an example of a function that's one-to-one and onto? Well, it turns out that the function f of x equals x cubed is one-to-one and onto. And you can see that it's onto because every possible value, vertical value, is attained by one of these things, right? I can always take the cube root, and that's the x value that gives me the value that I input into f to get where I want to go. And on the other hand, it's one-to-one. Well, it's one-to-one because, for a function, it has to pass the vertical line test. A one-to-one function has to pass the horizontal line test. We'll see in a second an example where that doesn't happen. Okay, so, for example, well, let's look at f of x equals x squared, even. So there's my axes. If I look at f of x equals x squared, shape is roughly this, right? And so what's happening? Well, there are definitely values. The same value gets taken on by two different points here, right? Because if I square something and it's negative, they both go to the same value. Okay? So this is not one-to-one. And it's not onto either because I can never get a negative value, so nothing here gets attained. Okay, whereas x cubed is one-to-one and is onto. Okay, let's try to do some that are just one and not the other. So try to think of one if you can. Can you think of a function that is one-to-one but not onto? Of course, I can't tell you whether you're right or not because there are lots of different possibilities. But here's one that comes to mind for me, which is if I think about the function e to the x, right, then what does it do? Right, it goes through 1, and so f of x equals e to the x. Certainly, it's 1-to-1. It passes the horizontal line test, but it doesn't actually get to any negative value, so it's definitely not onto. So this is 1-to-1, not onto. And can you think of an example of a function that is onto but not 1-to-1? You might want to pause. This is maybe a little bit harder. So let me draw some axes here. Well, here's one example. If I just want to look at cubics, I can look at the function f of x equals x cubed minus x. Right now, x cubed minus x, what is that? Well, that's x times x squared minus 1, which is x times x minus 1 times x plus 1, right? So this definitely has zeros at 0, -1, and 1. So if I plug in my zeros here at -1, 0, and 1, and I know that basically it looks like x cubed, that means that the function itself must do something like this. Okay, and so you can see that it's not 1-to-1 because, for example, there are 3 values, 3 inputs that give you 0, so it doesn't pass the horizontal line test right at the axis, but it is onto because I can get to any value. Okay, so this is onto, but not 1-to-1. Okay, so those are some examples from just ordinary functions that are 1-to-1 and onto. And in the next slide, we'll look at examples for linear transformations. Okay, so now let's think about 1-to-1 and onto for linear transformations. So the definition is exactly the same, right? A linear transformation is called 1-to-1 if whenever t of x equals t of y, so things are equal over in the target, then they couldn't have come from different vectors. They must have come from the same vector. Okay, so there's only one arrow going to any point over here. Right? T is called onto if for every b there exists an x such that there exists a preimage. So I'm over here, and I can always find something over here where the transformation took me there. Okay? So that's how a 1-to-1 to onto work for linear transformations. But we'll look at some example here. So suppose I've got this function. Now it's a matrix, right? So I'm thinking about it as a matrix transformation, which means what does this matrix transformation do? It eats what kind of vectors? Well, it has 3 columns, so it has to eat vectors of length 3, right? And so it eats x1, x2, x3, and it spits out the linear combination x1 times this column plus x2 times this column plus x3 times that column. Okay? So, y is, so I guess I should write some things down so that you've got a record of what we were thinking about here. So for 1, what's going on is, well, okay, so I'm adding, so I can get anything, right? So if I think about this as like a times x is going to be x1 times 1, 0 plus x2 times 1, 1 plus x3 times 2, 1, right? Now, even if I'm just allowed to make any linear combination I want of x1 of 1, 0 plus 1, 1, that means that in the output space, so now this is my output of my linear transformation, what can I get? Well, I can get anything, x1 times 0, 1, right? So I can get, here's, x1 times 1, 0, and now I can x2 times 1, 1. So that means I can get anything like this, right? Here's 1, 1. And now think about it, right? I mean, by parallelogram law, I can just get, I can get that thing, and I can get, this thing. And if I keep drawing it out and just figuring out how to tile things, then you see that what I end up getting is, and so on, that really I can get any, if I use the integers, I can get any integral combination clearly this way. But because I can rescale by real numbers, I can actually get anything in between. So clearly just the span of this vector and this vector is all of R2, and so that means it's onto. Okay, so it's clearly onto. Right, another way you could do it is you could think, okay, what happens if I try to take this matrix, so 1, 1, 2, and I've got a B1 here, and 0, 1, 1, and I've got a B2 here, right? So now I do row reduction, and what would ultimately happen is I'd end up with a pivot in this row and a pivot in that row and a free variable, and so there's no way to get zeros on this side equaling to non-zero on that side. Okay, so that means I'll always have a solution, and in fact I'll have infinitely many solutions, which means that it's not one-to-one. Okay, because I have a free variable. But thinking about it, you know, if you want to, somebody says, show that the following linear transformation is not one-to-one, a very simple way to do it is to say, well, okay, to show you I'm not one-to-one, what happens if I take 1, 0, 1, 1, and 2, 1, and if I multiply it, so notice that this column plus this column equals that column, right? So that means that if I apply this to 1, 1, 0, whatever that output is just this column plus this column, which is 2, 1. But of course, that's also equal to 1, 0, 1, 1, 2, 1, right, times 0, 0, 1. Because when I apply 0, 0, 1 to this, I also get 2, 1. So that means I've got two different input vectors that give me different output vectors, so it's not one-to-one. Okay, so this one is clearly onto, but not one-to-one. All right, so that's one. How about this matrix, which is a 3 by 2 matrix? So, well, let's see. We've got 1, 2, 3, and 1, 1, 1, right? So neither one of those vectors is a multiple of a scalar multiple of another, so they're linearly independent. So they look like this. They're two vectors in R3 somewhere. So they may not line up with the axes or anything, but it doesn't matter. Those two vectors in R3 are going to span a plane. Okay? And so it certainly won't be onto because I won't be able to get everything. Right? There's no way for me to get things that are not on that plane. So I claim that it's easy to see that 2 is not onto, since when I look at all the outputs, if this eats a vector of size 2 and just spits out the linear combination of these two vectors, right? Since columns of the matrix span a plane in R3, not all of R3. Okay? Now, on the other hand, you could ask, is it one-to-one? And the answer is yes, right? And so how would you see that something like this is one-to-one? So let me give you the argument, right? Suppose, to show it's one-to-one, I'm saying, well, what happens, right, if I take 1, 2, 3, 1, 1. Actually, I don't need to do it with specific vectors. Let me just call the vectors of this, the column vectors here, u and v, right? So I've got u and v. The abstract argument is even more convincing than the specific argument. So that means I'm saying, okay, so I'm taking this matrix uv and I could multiply it times ab. I can take this matrix uv and I can multiply it by cd. So in one case I get au plus bv. The second case I get cu plus dv. So if these two things were equal, right, if they were equal, then what would I get? Well, I'd get that a minus c times u plus b minus d times v was equal to 0. Right? But u and v, we just decided, were linearly independent because one's not a scalar multiple of one another. Okay? So since u, v, linearly independent, a minus c equals 0 and b minus d equals 0. The only possible linear combination I can get is where both of those things are 0. So that implies that a equals c and b equals d. Right? So that means that these two vectors were originally the same point. So I said, suppose they ended up at the same place, well then these guys had to be the same point. Right? So I'm exactly using the definition of one-to-one there. Okay, so let's look at another example. So this third example, what have we got? So tell me, to stop for a second and think, is it onto? Well, look at the span of these columns, right? If I take the span of the columns as the set of all things I can get, I will always get 0 in the last component, no matter what weights I put here, x1, x2, x3. I will always get, right? So I'm thinking about this as being multiplied times x1, x2, x3, right? So I get x1 times this column plus x2 times that column plus x3 times that column. I still get 0 down here. So clearly I only get things with 0 in the last component. That's not all of R3, right? That actually means everything is in the xy plane, if you will. Okay? So second question, is it 1-to-1? Well, no, because one of these vectors is a scalar multiple of the other, right? So they're not linearly independent, which is what you need for it to be 1-to-1. Or if you wanted to be more careful, you could say, well, okay, if I let x1, x2, x3 be 2, 0, 0, then the output of this will be 2, 0, 0. But if I let it be 0, 1, 0, the output of this will also be 2, 0, 0. So I can get 2, 0, 0 in two ways. Okay? And so finally, let's look at a kind of generic example. So here, these blue squares are meant to be pivots, right? So they're non-zero. And what does that mean? So you can see, actually, that if I ended up with a row-reduced echelon form like this, with a row of zeros at the bottom, this is just for the matrix, not an augmented matrix, then clearly I don't get everything, right? Because I only get things which have 0 in the bottom component. On the other hand, if I did get rid of that row of zeros, then I'd be good. Right? I can't cover things over here very effectively. But if I could get rid of this row of zeros and I only had the matrix, the 3 by whatever matrix here, it was missing its bottom row, then it would be onto, because there'd be no way for me to get a contradiction if I put B1, B2, B3 as a right-hand side here, because I've got a pivot in every row. Now, is it 1-to-1? Well, 1-to-1 means that I can't get the same output in more than one way. But here, I can get the same output in lots of different ways because I've got all these free variables, right? So every free variable means that I get infinitely many solutions when I try to solve this matrix times a vector equals another vector. Okay? So that's what's going on with the linear transformation situation. Okay, so now let's look at a little bit more theory that will help us sort out when something is 1-to-1 and onto for the case of specific matrices. So here's a kind of remarkable property that isn't true for functions in general, but is true for linear transformations. And that is that a linear transformation from r to the n to r to the m is 1-to-1 if and only if the equation t of x equals 0 has only the solution x equals 0. So you may remember that that was our definition for if this were ax equals 0, right, then we were saying that the homogeneous system has only the trivial solution, right? So that's another way of phrasing that in terms of matrices. But, I mean, what it's really saying is saying that t of x equals 0 is only the solution 0. We know that t of 0 equals 0 because we showed that in an earlier video lecture. So we know that t of x equals 0 has one solution always. It always has the 0 solution. Saying it's the only solution is precisely saying that the linear transformation is 1-to-1 at 0, right? 1-to-1 at 0. And the amazing thing is that if it's 1-to-1 at 0, then it's 1-to-1 everywhere. So you only need to check at 0. Definitely not true for other functions, right? Being 1-to-1 in one place doesn't imply anything about 1-to-1 in some other place. So it's an amazing thing about linear transformations. And it's really an algebraic property. You might see something like it again in abstract algebra if you take that course. So you think about how to prove this theorem, it's obvious that if it's 1-to-1 in general, right, that it's going to be 1-to-1 at the origin, right? That's all that that's saying. But saying that if it's 1-to-1 at the origin, then it's 1-to-1 everywhere, that's the part that's more amazing. So why should this be true? Well, suppose, so now I'm trying to prove this direction because the other direction is obvious, right? So I'm trying to prove that it's 1-to-1 at 0, and I want to show, so suppose that t of x is equal to t of y, right, for some x and y in r to the n. Okay? Well, that implies that t of x minus t of y equals 0. And by linearity, that implies that t of x minus y equals 0. Right? So you see, this linearity property is amazing, right? Because now I know that t of x minus y equals 0. But now I can say, well, I'm assuming this part of the theorem. I'm assuming that this t of something equals 0 has only the solution x equals 0. So that means that x minus y equals 0 by hypothesis. Okay, but that implies that x equals y. Okay, so there we go. It's not long or very hard. You just have to use the properties that you have, and you can show that it's one-to-one everywhere. Okay, so that's one example of a very helpful theorem. And now, let's think about what one-to-one and onto mean for matrix transformations. So suppose that t is given by, I know that every linear transformation is a matrix transformation, but here I'm assuming I know what the matrix is A, right? So proposition A says that t is one-to-one if and only if the columns of A are linearly independent. And we basically saw that argument in the previous slide already. And B says that it's onto if and only if the columns of A span R to the M. Okay. So neither of these is hard, but maybe it's worth writing down a little bit of an argument just so that you get used to seeing how these things get written out. So, okay, so that's the end of the proof of the first thing. So now let's take a look at A, right? So really there are two directions to each of these statements. But to show that the columns, if t is one-to-one, right? So really it's the same argument as before. So if t is not one-to-one, so to show this direction, I guess I'll say if t were not one-to-one, then we would get t of x equals t of y. But what are t of x and t of y? This is equal to x1 times the column vector a1 plus plus xn times the column vector an is equal to y1 times the column vector y1 plus ym times the column vector am. And this is equivalent to saying that x1 minus y1 times a1 plus plus xn minus yn, sorry, these should all be n's here, is equal to 0. Right, so if t of x equals t of y, then we get that this is true. Right, so if it's linearly independent, then that forces x to be equal to y, because x1 will be equal to x1 minus y1 will be 0, and xn minus yn will be 0. Okay, and so really this is the key connection. It's what we wrote out earlier that shows you how one-to-oneness corresponds to the columns of A being linearly independent. Okay, on the other hand, if the columns of A are not linearly independent, then we can find a value here such that this is equal to 0, right? Some linear combination of these things is equal to 0, and then we can use that to go backwards to find values such that t of x equals t of y. And to show B, what's happening? Onto if and only if the columns of A span R to the M, well, right, t of x is equal to x1a1 plus xnan. Okay, so if the columns of A span R to the M, then that means that I can always find x1 through xn that make this equal to some b that I want it to be equal to. Right? So if they span R to the m, then t of x is equal to that, so it's onto. On the other hand, if t of x is onto, then that means that I can always find some x that does this, and then this linear combination of the columns has to be equal to b. So really, at the end of the day, you're just writing out the definitions and following your nose. And so I've done some other examples, but maybe it's worth pointing out that, so if I want the matrix to represent a one-to-one transformation, then there have to be no free variables, right? Because if I have free variables, then by definition, I have infinitely many solutions to ax equals b, and for at least for some b, and then it's all hope is lost of it being one-to-one. On the other hand, onto means there's a pivot in every row, and that's again what we saw in the example on the previous slide, right? That if we had something like this, where we didn't have the bottom row, so we had a pivot in every row, then we can never get 0 is equal to something else. So no matter what b1 through bm I put on the right-hand side, I can always find the solution, as long as I don't get a string of zeros. Okay? So pivot in every row is the same thing as onto, and one-to-one is the same thing as no free variables. And those will be useful to us later on when we start to think about invertible matrices in a few lectures. So thank you very much for your kind attention.